All right, so this was Einstein's, another one of Einstein's famous thought experiments, is, an elevator sitting on the surface of the Earth turns out to be no different than an elevator being accelerated upward with the same acceleration that the Earth gives a falling object, right? The Earth, for when you drop something, it falls at a very famous 9.8 meters per second per second. So it's getting faster by 9.8 meters per second every second that goes by. The object falls. Right? So if you're accelerated upward, gravity for somebody in that elevator that's accelerating through space, let's say, so this is out in space, if there's a constant acceleration of what we call 1g, the acceleration due to the Earth's gravitational field, just some external object pulling up, the person inside of the elevator, as long as there's no window or anything like that, would not know whether they're standing on the Earth or being accelerated out in space. So that was Einstein's, that led Einstein to these ideas of general relativity. And so in general relativity, it turns out that mass bends or curves space and time. And so here's one of the things that Einstein realized is think about this elevator for just a second. And if you had a flashlight over here on one side, this person inside of the elevator, as you turn on the flashlight, then of course the light goes pretty fast. Obviously, this is a small little space, but because this thing is being accelerated upward, then when the light beam first takes off, when the photons first travel, they're not going to strike the wall on the other side exactly in the same spot as they would if the accelerator were at rest, for example. So the difference between accelerated motion and motion either at a constant speed. See, if this thing was traveling at a constant speed, well, if they were traveling at a constant speed in space, that's actually what would that's the zero gravity that you would experience. That like, for example, the people in the space in the International Space Station experience, right? Roughly zero gravity. So if it's moving at zero or moving at a constant velocity, the beam of light. Let me get my mouse back over here. The beam of light would just simply travel right across. But because it's being accelerated, as the light travels across, what happens is the elevator moves up a little bit, and so it would strike the floor. It would strike a little bit closer to the floor, just a slight amount closer to the floor. Einstein said, well, wait a second, if that's taking place on an elevator in space that's accelerated, well, what about an elevator on the surface of the Earth? Would a light beam curve on the surface of the Earth just like it would do in an elevator in space? And indeed, it does, exactly like Einstein predicted. And of course, he has equations that describe all this. And so this is now this is the modern theory of gravity. Okay, in fact, because of Einstein, in his 1916 paper on general relativity, we no longer think of gravity as a force the way Isaac Newton thought of it. It is rather a warping or a bending of space-time due to matter. Right? The more matter you have, the more space and time is bent. So this idea that some things don't travel in exactly a straight line, or really what a straight line is curved in the vicinity of a massive object. And of course, what this leads to, the most extreme example, is the most massive object you can possibly imagine would be, of course, a black hole. Where just imagine this as like a those. What am I trying to think of the word. You know those things that people bounce on in their backyards. They set them up a trampoline, right? Like a trampoline. And so if you put like a little rock, just a small, moderate-sized rock, the trampoline will bend a little bit, curve a little bit. If you put a really massive rock in the middle of the trampoline, it'll bend even more. And then if you put a boulder, something that weighs many, many tons, the trampoline is not meant to hold that kind of weight, and so it tears a hole through the trampoline. That's just like what a black hole does to space-time. Okay, so where the mass the mass density approaches infinity, right at the center of the black hole. And we have a name for that. It's called the point of singularity. That's also known as the center of the black hole. That would literally tear a hole in the fabric of space-time. So space-time would, that's kind of the way we think of these black holes, right? Okay, so that's here's the Michelson-Morley experiment. I mentioned that before. Einstein claims to have never even heard of it. It doesn't really matter. I mean, whether he heard of it or not, he came up with this brilliant idea, which was actually, in hindsight, was verified by the Michelson-Morley experiment. This was kind of it was pretty advanced for the time. It used some of the techniques that we still use today. This idea of what's called interferometry. I won't really go into that too much, but anyhow, it was a very clever little experiment in the late 1800s. All right, so the gravitational effects. This is something really important to understand. Is if you go out, so remember, let's take a look at this. From the center, from the point of singularity to right where the speed of light goes to, the escape speed goes to the speed of light, that would be called one Schwarzschild radius, right? So if you go several Schwarzschild radiuses away from the black hole, you just wouldn't even notice that there's this black hole right here. A big myth about black holes is they're just going to suck up everything around them, and they don't. The matter that comes close to the black hole will tend to form an accretion disk, right? Just like we saw with white dwarfs, with neutron stars that form accretion disks. This matter is moving around in an orbit around the event horizon of the black hole, and in fact, that matter will actually rub against itself, and that's how we know about the black holes. Okay. All right, so let's go into this. And here's another thing about, people often like to think about black holes and what would it be like if you could fall into a black hole. It would be terrible, okay? It would be absolutely terrible. So there's this thing called the tidal effect. This is something, you probably experienced if you've ever gone to the beach and stayed a couple of days. You'll notice, of course, there's high tides and low tides, and that is really mostly due to the moon pulling on the Earth, and it pulls on one side of the Earth stronger than it does on the other side, right? The side that's closest to the moon is pulled a little bit harder than the other side of the Earth, and so that's called the tidal effect. That's why we have the tides, or at least partially why we have the tides. The sun actually has a little bit to do with that, not a little bit, about half as much to do with the tides as well. Anyhow, that's a different story. So because of this idea of the tidal effect, as you're approaching a black hole, the amount of force between molecules that basically hold molecules together, like in your body or in a spacecraft or something like that, would be so extreme that the individual atoms would be torn apart as an object approached a black hole, as it got closer and closer to a black hole. The tidal effects would be so enormous that the object would be just torn apart and fall into the black hole in a if it was heading in that direction towards the black hole, it would just fall into the black hole as a stream of unassociated atoms. And that's no way, you're not going to survive something like that. All right. So and one of the effects, of course, let's get into this, is there is this thing called the gravitational redshift, which just has to do with gravity, right? Like if you take a photon here. Here's a good example right here. So you take a photon that's getting really, really close to the black hole. So it's not reached the event horizon yet. For it to leave the black hole, it's still traveling at the speed of light. Don't forget that. Everything always travels at the speed of light. That's what Einstein's special theory of relativity is talking about. But what happens is, because it's close to a black hole, the photon loses energy. It's not slowing down or anything, but it's losing energy. And of course, when we lose energy, that's called redshift, right? That's exactly the idea of a redshift. And so there is gravitational redshifts that take place near black holes, and we can actually measure that. We can measure that not with respect to a black hole, but with respect to just any massive object. We can actually measure these gravitational redshifts. As far as what's inside of a black hole, nobody really knows. I mean, the black hole is this incredibly dense object. In some sense, the density approaches infinity. The problem is, if you have quantities that approach infinity, we've found this time and time again in physics, is there's something wrong. There's something wrong in our equations. When something adds up or approaches infinity, there's just we just don't understand what's going on. So whatever is going on inside of a black hole, we don't quite understand that. These are very extreme conditions, as it says, and to some extent, it's still a great mystery to us. But we do know that when a star more than 8 times the mass of the sun, dies, undergoes a supernova explosion, creating all the heavy elements beyond lead. Beyond iron. But long after the supernova explosion, if what remains is more than 3 times the mass of the sun, then nothing can stop it from collapsing. Gravity that's the ultimate win for gravity. Gravity squeezes that object into what we would consider a black hole. So here's something interesting that we actually use this all the time. Near a massive object, including black holes, the light actually is bent, and we use that. In fact, it's called gravitational lensing. So it's like a lens, like the way the lens bends the light. We can actually use that with the gravitational forces. In fact, this was our very first candidate for a black hole. It was called Cygnus X1. And Cygnus X is an actual star that can be observed, and it actually has a companion. Cygnus X was, I think it's like 25 times the mass of the sun, and then there's a second object which you can't actually see the object. You can see the matter around the object, but you can't actually see this thing called Cygnus X1. This was actually first detected in the 1970s, I believe. All right, so that was, you know, we've found lots of these since then.